Hello everyone. So today we're going to talk on the binary adders. So adders are very important in microprocessors or controllers or any kind of processors. If we take uh, the main thing is a ALU, that is arithmetic and logical unit. So in that arithmetic and logic unit there is a adder which adds these binary, because all these processors and these computers, everything will works on ones and zeros. So basic addition is very much important. So let us hit back to the screen and see the basic half adder and full adder. So adder is one which performs the addition of two numbers. So the two numbers which we are talking about here is in terms of binary. So as we all know that the binary numbers, say if we add a 0 with 0 we get 0, and when we add 0 plus 1 we will get 1. But when we add 1 plus 1, it is not the OR operation, it is the addition operation. So it's a binary addition. So the maximum value we'll get as 2. So we have to subtract this by 2 again. So we'll get 0 and we'll get a carry 1. So we have, when we add the two inputs here, we have the two outputs, that is sum, and we call this as carry. That is sum and carry. So there are two types of adders here. One is the half adder and full adder. So half adder is one where we consider there are only two inputs and two outputs, and full adder is one where we consider that we have the three inputs and two outputs. So three input is one. In performing these additions, whatever I have done, that is 0 plus 0, it means we have the two inputs, say A and B. So we have considered, but we have not considered any previous carry. If we consider that previous carry Ci, so then it will become a full adder. It will act as a full adder. It means we are considering the carry as well as the input, the previous carry as the input for the next addition. So that will become a full adder configuration. So where we have the three inputs and the two outputs remains to be same as sum and carry. So now let us look into these, each of these, half adder and full adder. So let us write this half adder. So as I said, half adder has the two inputs and two outputs. So we'll write that as a representation of a black box. So this is a logical circuit. We don't know what exactly there is inside, but we have to figure out, we have to design the circuit for this half adder so that it will give the suitable output for me. So this is my A and B, and this is my sum and carry. So if you write the truth table here, so this is A and B input, and the outputs are sum and carry. So with the two inputs, the possible combinations that we can write is 0 0 0 1 1 0 1 1. And if we add these numbers, so 0 plus 0 will get 0, carry 0, 0 plus 1 sum 1, carry 0, sum 1, carry 0, 1 plus 1, we know that the sum is 0 and carry is 1. So let us write the Boolean expression for this sum. So we have to take only the ones which are here. So let us take only ones which are here. So if I consider these ones, then I'll get an expression here that for sum is equal to A bar B plus A B bar. So this is nothing but an exclusive operation. So this can be written as A exclusive B. And carry is, I have to write, there is only one output, that is for one I have to write. So this is nothing but A into B. So it means a simple AND operation. So now I can write from this expression my logical circuit. So my logical circuit is just an XOR gate. So this is my input A, B, and this is my sum output. And I'll take from here, I'll just tap from A and B and connect to my AND gate. And So this gives me carry. So this is my half adder circuit, the box which you had written. So inside the box you can consider this is the logic circuit which is present. Now we can also realize this using the universal gate, that is the NAND gate and NOR gate. So let us see that quickly. I'll save this page. So let us realize the same thing with the help of NAND gate and NOR gate. I'll delete this. So if I want to realize this using the NAND gate, so let us take the NAND gate first. So we'll apply the involution law for this equation, that is for exclusive equation. So what do we get here is a B bar. So now let us apply the whole bar here. So let us break the inner bar here. So when we break the inner bar, so what do we get is that A bar into B whole bar into A bar, sorry, into A into B bar whole bar, and we have one more whole bar here. So this is perfectly in an AND gate form. So let us realize this. So we'll use we have the two inputs here. Let me write that. So my two inputs are A and B. So I'm writing for the sum. So let me get the complement of this. So this is my AND gate. So now this is my input A, so here I'll get here A bar and here I'll get B bar. So let us get the first component here, that is A bar into B. So A bar is this and B is I'll get from here. So I'll get my AND gate here. So likewise that is A into B bar. So I'll take one more line from here and I'll connect here. So this I'll get. So here this is A bar into B whole bar. So here I will get this as A into B bar whole bar. So fine, now I have to combine these two with the help of the one more NAND gate, and there I will get my sum output. So this is perfectly in the sum form. So now I have to obtain the for carry I have to obtain, so it's simple double bar. So I have to realize this with just a double bar here. So now I'll take the two inputs here. So this is my A and B. I'll connect here. So this I'll get this as A into B bar. So connect once again, you complement this with one more NAND gate here. So I will get this as A into B. So this is my carry output. So this is the NAND gate realization. So NOR gate realization, I'll leave it to you. In the previous tutorial we have done the NOR gate realization, so use it. So bring the sum and carry in the NOR gate form and realize it. So that's it. So now we will talk on the full adders. So as I said before, the full adder is a circuit where it has three inputs and two outputs. So I have three inputs here. So this is my A, B and Ci, and my outputs are sum and carry out. We call this as C out. So if you write the truth table for this, let us write the truth table here. So this is A, B, Ci, and then the sum and carry. So let us write all the possible inputs here. So here I'll get this as 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1 0 1 1 1 0 1 1 1. So these are my inputs here. Now what is the sum that we'll get here? So here I'll get 0, the carry is 0, sum is 1, carry is 0, sum is 1, carry is 0, sum is 1, carry is 0, sum is 0, carry is 1, sum is 0, carry is 1. For all the three inputs 1, so I'll get sum and carry as 1. So now let us write the expression for this here. Let me write it here. So I have to take for only ones of the sum. So I have these 4. I'll take it. So for the sum expression will be, that is, sum expression is A bar B bar C plus A bar B C bar plus A B C, sorry, not A B C, A B bar C bar, and the last one is plus A B C. So now let us take the common terms here. So if I look into the first term and the second term, the common terms are A bar. So I'll take the common term A bar. So I have here B bar C plus B C bar here. Then the common term in the second thing is, in the second last two term is A. So I'll take this as A common. So this is B bar C bar plus BC I'll get. So this we can think of as one more new variable, that is of D. If I call this as D, and this is nothing but D bar. Why? Because this is a XOR and this is XNOR. So XOR and XNOR, only thing is that it is a complement of each other. So I can write this finally as A exclusive D by A bar, this is A bar into D plus A D bar. So when you substitute finally, so then we can get this as A exclusive B exclusive C. So this is the expression for the sum. Now let us look into the carry. So carry has many forms. Now let me write for carry C. So I have to take the 1 2 3. I think we have missed one more, that is for 0 1 1. We will get this as 0 and 1. Okay, so even we have to take this one. So in that case we have here that what we have here is A bar BC plus A B bar C plus A B C bar plus A B C. So now we know from the Boolean expression that A plus A is equal to A, or A plus A plus A plus A. You add as many as A, still it results in A itself. So it means it will not be harm if I write there are multiple similar kind of terms. So let me write here for ABC as plus additional terms. So I'll write this as plus additional term. I'll add it for simplicity, ABC plus ABC. So ABC plus ABC plus ABC is only equal to 1 ABC. So there is no harm writing this into 3 terms, another plus 2, another such terms. So I'll take this term and this term. What are the common things here? So I'll take BC as common, then I have here A plus A bar. And then I'll take this and this terms into common consideration, then I'll take AC as common. So I'll get this AC of, then I'll get B bar plus B, then plus I'll take this term and here this term, then in this I have AB as common. So then I'll write this as C bar plus C. So we know from the Boolean theorem that A plus A bar is equal to 1, likewise B plus B bar is equal to 1, and C plus C bar is equal to 1. Then finally, if we rearrange this equation, I'll get this as AB plus BC plus CA. So this is my expression, the logical expression for carry for a full adder case, right? So now if we write this, the circuit here, so if I try to write this with a 2 input XOR gate, if this is my A and B, so then I can combine this with one more input here, that is Cin. So I'll get this my as output. So this is my sum. So this is the Ci. So now remaining terms are the basic AND operations. So here I'll take this as A into B, perform the AND operation, then B into C, let us take here, A into B, B into C, then C into A. C is this term and A is this term. I'll tap here itself, this is my A, and I'll tap from here, this is my C. I'll get this here. So then finally combine using an OR gate. So this is my carry. So this is my carry C. So this is the logical circuit for the full ladder. So now let us realize this using the NAND gate and NOR gate of full ladder. So let us realize this full ladder using the NAND gate. So I'll write here realization of full adder using NAND gate. So now let us write the expression for this full adder here. So we have the sum is equal to before going to the NAND gate realization of this, let us talk about realizing this using two half adders. So let me clear this everything. So I'll write this as realization of full adder using two half adders. This is very important. So in the exam it may come, so realize the full adder using the two half adders. So how do I do that? So I know a half adder is a circuit which has one half adder is a circuit where it has one XOR gate and one AND gate. So this is your basic half adder. So this is our basic half adder. This is sum and carry. So how do I use two such half adders and obtain my full adder circuit? So to obtain that, so I have to go back to my carry. So I have to rework with my carry expression here. So let us take the carry here. So the carry expressions are A bar BC plus A B bar C plus A B C bar plus A B C. So now I have to realize this again, once again, in a different way, to use the half adders. To realize this, let me see what is the common term in first two. So first two common term is C. So let me take this as C as common. So here I'll get this as A bar B plus A B bar plus. Now what is the common term in the next thing is, so A into B is the common term. So here I'll get this as C bar plus C. So C bar plus C, as we know, it is equal to 1. So finally I'll get here, this is equal to C into A exclusive B, is nothing but A exclusive B plus AB. Right, now I have the two XOR gates and two AND gates. I have to use this and I have to realize the uh, my half adder. So how to realize this, my half adder? The sum expression remains to be same because there is no change in the sum. So sum is nothing but A exclusive B exclusive C. So it means I can perform A exclusive B, then I can perform that resultant with the exclusive with the C operation. So that is fine. So then now let us use this two half adders here. So this is my A into B, and let us connect to next half adder input. So I have the third input here. So this is my CI. So for the carry, I'll take from A exclusive B into C. So A exclusive B is this. I'll take this into C. C is this. Then there is one more term, that is A into B. We know that one of the half adder we have this. So now only thing is that we have to combine these outputs. That's it. Using an OR gate. One additional thing that we'll get is the only OR gate. So this is my carry, this is sum. So how do we say that this is the, so if I draw, so what is this? This is my one of the half adder. Then this is my another half adder, right? So half adder is a circuit where it consists of one XOR and one AND gate. So I utilize this, and by utilizing these two half adders, I have designed my full adder circuit. Okay, so next we'll talk about I'll leave the full adder realization using the NAND gate to you. So only thing is that you all have to apply the double bar here and to it as an assignment. So next I'll move on to the parallel binary adders. So in parallel binary adders is nothing but it is the extension of the full adder. Now for example, in the previous whatever we have done full adder, it is just 0 plus 1, and if this is nothing but your A and B single inputs, single bits, and if there is any carry C in, we have considered either it is 0 or 1. So based on that, the output will also be, what we get here is 1, or we'll get the sum as 0. So likewise, this is okay for 1 bit, but in real problem, in reality, there is no 1 bit addition that we'll do. Basically, we will do the addition in terms of nibble wise or byte wise, or maybe word wise. So let us take an example of a nibble. Nibble is nothing but the combination of 4 bits. Now let us say we want to perform an addition of 2 with 5. We represent these 2 and 5 in terms of 4 bits. Now we represent this in terms of 4 bits as 0, 0, 1, 0, and this is 0, 1, 0, 1. So when we add these two, what do we get here? So this is 1, this is 1, this is 1, 0. Fine. From each of these addition, I get the sum here. So carry is 0. So sum is 1. So I'll split this and write in a different way. 0, 0, 1, 0, 0, 1, 0, 1. Right? So this is nothing but my A and B. So now in this case, this is my A and this is B. So if you split this, if you convert this decimal to a binary numbers, so then these positions we call it as A0, A1. This is actually A, that is fine. But in terms of bit levels, if you write, that is A0, A1. So this is A2 and A3. So likewise, this is B0, B1, B2 and B3. So now let us perform the addition. So when I perform 0 plus 1, so initially the carry is considered to be as, I'll write here the carry inputs Ci, Ci. So carry inputs, so consider that the carry input is 0. So what is my sum output here? It is 1. So this is my S0. So what is my C0? So C0 remains to be 0. Okay. So now this 0 will go back here and it will be considered as C in for the next addition. So then it is 0 plus 1 plus 0. So I got the sum as 1. So this is my S1 and carry is again 0. So that is my C out. One more C out. So C out, or I can write this as C out 1. So this acts as again input for the next addition. So then I'll add 0 plus 1. I get sum as 1. So that is my S2 and I got the carry as 0. So this carry I can call this as a C0 2. So this carry is added here in the next addition. So then 0 plus 0 plus 0, I get 0. So my S3 is 0 and my C03 is also 0. So this is how basically an addition is performed. So for that, what we need to do is that we have to connect the series of full adders. So we have to connect the series of full adders. So if you take the full adder like this, so for this, how many full adders are required? Since I am performing 4 additions, so 4 full adders are required. So let me write from here. Okay, so these are my full adders. So 4 full adders, because there are 4 bits, so I need 4 full adders. That's it, as simple as that. If there are 5 bits, I need 5 full adders. If there are 8 such bits, then I need 8 full adders. So it's based on the number of bits I am adding at a time. So then I'll give my inputs as like this. So this is my A0. As I had written, in the same way I have to give the input A0 and B0. And I have one more extra, that is, I'll call this as C in. Let us avoid the confusion here, so I'll call this as Ci0, and the first sum output I'll get, that is S0, and this output whatever I get here, so that is my C0 0. So this is connected back to the input here to the next section. So next section, apart from that, we have the two additional inputs, that is A1 and B1. So now this is B1. So this C0O will become CI1 for the next full ladder circuit. So next I'll get an output as S1. So here I got an output of C01. So this has become the input for the next full ladder. So then apart from this I have two other inputs. This is my A2 and B2, and this is my CI2. So then I have my sum here. So this sum is S2, and here my carry is C02. So this C02 acts as input for the next full ladder here, like this. So apart from this I have two additional inputs. So that is my A3 and B3, and this is CI3. So then final output I'll get here as S3 and CO3. So basically in between carries we do not use, and finally if we get any carry here we will consider. So since here there is no carry, so carry remains to be 0. In between carries it's not important for us as a result per se, but it is required for addition. So this is the basic parallel full adder circuit. This is a 4-bit parallel full adder circuit. So let me write a correct name for this. So this is actually called as 4-bit parallel adder, parallel binary adder. So if there are 8 bits, if A is of 8 bits, B is of 8 bits, then I need 8 such adders, binary adders. So then we call it as 8-bit parallel binary adders. So this is about the adders. Okay, then we'll wind up at this point, and next we'll talk on the multiplexers in the next session.